Hey guys, Miss Marusik here, and in this video we're going to talk about solving unknown concentrations of substances at equilibrium. And to do so, we're going to be utilizing Kc values and rise tables in order to organize our information. Now they give us on here kind of a series of steps that we can use to solve these problems. We're going to talk about these series of steps in the context of some examples. So let's go ahead and get started on that first example here. They give us here a reaction of H2 plus I2 with a reversible arrow going back and forth between 2HI. That reversible arrow lets us know that this reaction is capable of reaching an equilibrium state. They also give us the Kc value at equilibrium. They tell us it's 50.5 at 448 degrees Celsius. Just as an FYI, they tell us that temperature 448 degrees Celsius just to let us know that technically, that 50.5 is only true at that temperature conditions. If the temperature was something else, then that Kc value would be something different. So we don't actually use that 448 Celsius in our work. So then they give us some additional information here. They say, hey, hydrogen gas and iodine vapor were added to a previously evacuated flask, meaning I cleared everything out of the flask before I added these two gases in. The initial concentration of each of the two gases was equal to 2.00 molarity. And so what I'm going to do is I'm going to start to organize that information in a rice table. So you notice I came over here and put rice down. I went ahead and wrote my balanced reaction. And what I did is I included at initial concentrations for the I value that those initial concentrations of each of those gases was 2.00 molar. Now you notice that nowhere in the problem do they mention an initial concentration of HI. And as a reminder, anytime we have a substance that is not mentioned initially, we assume that the initial concentration of it was 0. So I went ahead and filled that in here. So then I also came over here and went ahead and constructed my Kc equation. I know that the Kc would be equal to my product, the Hi raised to its coefficient, over the reactants raised to their coefficient, here them both being a coefficient of 1. So I didn't have to write that coefficient, it's understood. So then I want to ask myself, okay, let's think about what we're trying to solve here. It says that the system was allowed to reach equilibrium at 448, meaning that this Kc value is going to be that 50.5. And we want to calculate the concentration of all three species present at equilibrium, meaning I'm trying to figure out what the concentration of each of these three substances would be once we reach equilibrium. So to do that, I'm going to kind of need to think about how things are going to shift around here so that I can kind of start to fill in some information on this table and then maybe utilize this equation here to help me solve what these unknown concentrations should be. So let's kind of process here. Right now, we only have reactant. There is no product, but I know at equilibrium, I should have a little bit of everything. And so with that said, to have a little bit of everything at the end, I know that this product is going to need to increase. Now, the only way that the product can increase is if I use some of these reactants to go and make that product. So what that means is that these reactants over here are going to need to decrease. Now, remember, all changes on these rice tables do so in mole to mole ratios. We've got to utilize those coefficients. So when I have this 1 to 1 to 2 molar ratio here, I should see that same ratio reflected in these changes. So let me go ahead and put up here what I filled in for the rest of my rice table. So what I said is that, okay, I know H2 and I2 both need to go down. And I put that they're going to go down by x and x, or 1x. Why 1x? Because they both have coefficients of 1 and 1. And so at equilibrium, that would leave me with concentrations of 2.00 minus x for both the H2 and the I2. However, we said that the HI needs to go up. But remember, it's got a 2 in front of it here. So to maintain that 1:2 ratio that we have with everything else, this has to go up by 2x, meaning at equilibrium, I would have 2x for my concentration here. Now, obviously, I need to figure out what x is, right? So what I'm going to do is I'm going to plug all of these in to this equation over here, because I also know that Kc value should be 50.5. So with all that said, let me go ahead and put up here my algebra, and I'm going to talk us through exactly what I've done here to finish solving this problem. Okay, so what I did first is I took the information from E here in my rice table, and I plugged it into this Kc expression. So for the HI, I plugged in 2x because that's what I had here, and so I squared that. And then I set that over H2 and I2. Now, H2 and I2 were both 2.00 minus x. So when I multiply 2.00 minus x times 2.00 minus x, that would be that term squared. And then I set what I wrote here in light purple equal to 50.5 because we said that's what our Kc value would be. So now what I need to do is start trying to solve this. And the first thing I notice is that both the numerator and the denominator are both squared. So if I square root that whole side, I can undo those squares. And remember, what I do to one side, I have to do to the other. So you can see here in pink, what I did is I square rooted both sides. And what that left me with is what you see here in this dark pink. The 50.5 square rooted gives us a value of 7.106. That is equal to 2x, because again, when I square rooted this, that got rid of that square, over 2.00 minus x, because again, when I square rooted up here, that got rid of that square. So then what I want to do is I want to get unknown variables out of the denominator. Remember, having x in the denominator is a terrible place for it. And so what I did is I divided here by 2.00 minus x. So I need to multiply by it in order to undo that. And what I do to one side, I would do to the other. Now, obviously on this side, that would end up canceling out, leaving me with just 2x remaining over here. On this side, in order to multiply these, I'm going to have to do some distributing. So what I would do is this 7.106 times 2, which would give me 14.212. Then I would have minus, and then the 7.106 times x, which gives us 7.106x. Now, to finish solving this, I would need to combine like terms. So what I did is I added 7.106 over to this side. That got me 9.106x, but then I would still have that equal to the 14.212 that's still over here on this side. So then, this dark purple equation here, what I would do is divide both sides by 9.106, and that would isolate x by itself. And that gets me that x is equal to 1.56. So here's the deal. Now that I know what x is, I can plug in x in for each of these and solve what these concentrations should be. So that's what I did here. So I said, hey, H2 was 2.00 minus x. Well, that means 2.00 minus that 1.56 I just solved for, and that gets a value of 0.440. And since it's a concentration, I would put a unit of molarity. I2 is going to be exactly the same thing because, again, we wrote the same thing for it up here. HI, on the other hand, was 2x. So I would need to do 2 times that 1.56, which gets us a molarity of 3.12 molar. Now, at this point, I kind of always ask myself, well, do my answers make sense? And, you know, with that product getting really, really big, that makes sense because that would support a Kc that's larger than 1. We know if it's larger than 1, then that should be product favored. But one of the other ways that I can actually double check this is by taking these numbers, plugging them back into here and seeing if it gets me a Kc value of 50.5. Now, I'll be honest with you, I think on this one, if you plug in these exact numbers back into Kc, I think it comes out to like 50.3. It comes out really close. Keep in mind that it might be a little bit off because obviously we did some rounding here and there, and so that could throw off that answer. But you should get really, really close to 50.5 if you go back and double check it. All right, let's go ahead and flip the page and look at another example. So on the top of the next page, we notice that we're going to be dealing with the exact same equation that we saw on the previous page, H2 plus I2 back and forth between 2HI. And we see that, again, we have that same Kc value at 448 degrees Celsius. So same temperature, same Kc value, all of that. So then it says here that hydrogen iodide gas was added to a previously evacuated flask. The initial concentration of HI was equal to 2.00 molar, so that's what I plugged in here. But you notice they didn't mention anything about H2 and I2 initially here. And so therefore I assumed that both of those were starting off at 0. And so again, I went and wrote my Kc expression. And so I plugged in my products over reactants, and hopefully this looks familiar because it's the exact same Kc that we saw on the previous page because it was the exact same equation. So then I want to think about, well, what's going to be going on this rice table? And so I say, well, look, I have only product right now. I'm going to have to shift some of that back to this reactant side because remember, I need a little bit of everything at equilibrium. And if I have no reactants, I need to take some of that product and shift it to that reactant side so I can have a little bit of reactant at equilibrium. However, remember, those changes are going to happen in mole-to-mole ratios. So with that said, here is how I filled out the rest of my rice table. I said that my HI is going to go down by 2x, again, because it has that 2 in front of it. And so at equilibrium, that would leave me with 2.00 minus 2x. My H2 and I2 would go up by x, leaving me at equilibrium with concentrations of x and x. All right, so now I'm going to take these equilibrium variables here and plug them into my Kc equation. Again, remembering that my Kc value was 50.5. So to see what's happening here, again, I plugged in my 50.5 for Kc here in purple. My Hi, we said that that was 2.00 minus 2x, and that would get squared because it was squared up here in my equilibrium expression. The H2 and I2 were both x and x. X times x would simply just be x squared. And I see the same situation that I saw on the previous page. I see that both the numerator and the denominator are squared. So to undo that, I can square root both sides here. Square rooting the 50.5, again, gets us 7.106. Here, square rooting eliminates these squares, so I end up with the 2.00 minus 2x over x. So again, that squared term went away. So now, again, I see an unknown variable in the denominator. Terrible place for it. We want to get it out. So I multiplied both sides by x. That would cancel out this x over here, but that would leave me with 7.106x on this other side, equaling the 2 minus 2x that we still had in the numerator. So again, I want to combine like terms. So I would add the 2x over to this other side. That would get me 9.106x equaling 2. So to solve for x, I would simply divide both sides by the 9.106, and that would give me that x equals 0.220. So now that I have x, now I can plug that in for all of these concentration terms. And so then that's what I did here for my final answers. I said that, hey, H2 and I2 are simply just equal to the X that we solved. So they're both that 0.220 value for the molarities. However, the HI we said was 2 minus 2X. So 2 minus 2 times that 0.220. And that got a value of 1.56 molarity. Again, if I wanted to double check it, I could take these concentrations, plug them back into Kc, and see if they equal anything close to 50.5. It may not be exact, but it should be pretty darn close. All right, let's talk about one more example that actually has a little bit of a quirk to it. All right, so on this problem here, we're going to be utilizing the same reaction we did up above, that same H2 plus I2 back and forth between 2HI. And we're going to have the same Kc value that we did up above. It's again at that 448 degrees Celsius, so we're going to have that Kc value of 50.5. But this time I'm starting out with a little bit of different information. It says here that the initial concentration of HI, H2, and I2 were each equal to 2.00 molarity, meaning I've got a little bit of each of these initially. So where this becomes a little bit more of a challenge is that it's not obvious which direction I'm shifting in. I don't have zero reactant or zero product to make it obvious I need to shift toward those. Here, with a little bit of everything, I'm going to have to do some figuring out of where am I currently at in comparison to equilibrium, and how am I going to get to equilibrium. To do that, what we're going to do is we're going to first figure out where is our ratio right now. How does our value right now of Q compare to K? So you notice here I wrote Kc equation, but I also wrote that this Kc equation could be used for Qc for any time I'm trying to calculate that product to reactant ratio. So what I'm going to do first is I'm going to actually plug in the data that we have right now into this equation to see if I can figure out the direction in which we need to shift our substances around. So when I do that, when I take these 2.00 molarity concentrations and plug them into this equation, I see that plugging all of that in gets us a value of 1. So what that means is that right now, my ratio is at 1. But remember what I want my ratio to be. The goal is to get to equilibrium. Well, at equilibrium, that ratio is 50.5. So in comparing the 1 to the 50.5, we can see that right now my Q value is less than my K value. If K is 50.5 and I'm at 1 right now, then that means my Q is too small. So in order to get that Q to increase so that it can equal K, so that the 1 can become 50.5, I need to get it to increase. So think about what I would want to do to get the ratio to increase. What would I want to do to these concentrations? Well, if I want to get that number to be bigger, the way I would get it bigger is by increasing my numerator. Now, the numerator are the products. So therefore, I need the products to increase. I want to shift towards the product side of this equation. Now, in doing that, I would end up using up some of the reactants. So not only will my numerator become larger, but the denominator will become smaller. So my reactants will decrease. Now, let's say you calculated Q and you had the opposite. You had something that was too big. Maybe you had 100 for your Q. So to decrease it, I would need to do the exact opposite. I would need my reactants to increase at that point and my products in the numerator to decrease. So you always have to ask yourself, where is my ratio at right now? And what do I need to do to shift things around to get that ratio to what I want it to be? So now that I know I'm going to be shifting to the product side, I can come over here and start filling out my rice table. I can say that, hey, we said that we want the products to increase. So you notice I put plus 2x over here, leaving me at equilibrium with HI equaling 2.00 plus 2x. My two reactants, I want them to decrease. And so that would leave them at equilibrium at 2.00 minus x. And so now that I have those equilibrium terms, I can now plug them in to my QC formula along with the KC that I'm trying to solve for, which is the 50.5. So in plugging everything in here, what I would have is, again, my KC would end up being 50.5 because that is still consistent. On top here, I would have my HI, which again we said is 2.00 plus 2x. That would get squared because it had that coefficient of 2 as we wrote up here for that exponent. On the denominator, I would have 2.00 minus x times the other 2.00 minus x. And so that leaves me with 2.00 minus x squared. I see I have a square on both the numerator and denominator. So to undo that, I would square root both sides. In square rooting 50.5, that leaves us with 7.106. In square rooting this other side here, I eliminate those exponents of 2. Okay, so now I want to get my unknown variable out of the denominator. So I multiply both sides by 2.00 minus x, which of course undoes that over here. So that's all canceled out. So that leaves me with 2.00 plus 2x. Here, when I distribute the 7.106 to both terms, that leaves me with 14.212 minus 7.106x. And so now I would want to combine like terms. So what I chose to do is to combine all of the x terms over here and to combine all of the non-x terms on this side. So when I bring that 7.106x over, since it was subtracted, I added it over. To bring the 2 over, I subtracted it. And so that left me with 12.212 equals 9.106x. To solve x, I would simply just divide both sides by that 9.106 value. That gives me an x of 1.34. So now that I finally have x, now I can use that to solve what these concentrations were at equilibrium. So remembering that x is 1.34, here's what I did to finish solving this. I said that, hey, H2 and I2 were both 2.00 minus x, x being 1.34. So that leaves me with ending concentrations of 0.66 molarity for both of those. On the HI, it was 2 plus 2x, so 2 plus 2 times that 1.34, and that gets me an ending concentration of 4.68 molarity. So we were able to get all three of those molarities the same way I did on those other problems. It was just that first, in order to figure out the direction I'm shifting in, I needed to first solve my Q. I needed to ask myself, where is my ratio currently and what do I want to get it to? And to get it to that, how do I need to shift things around? You're going to have to make those hard choices before you try and solve a problem like that. All right, I hope we're starting to feel more comfortable with utilizing rice tables to organize our information. By the way, all of the work that I've been showing you with the rice tables and such is how you would want to show it on your work for the AP test. Your AP graders are going to expect to see that information organized so that they can tell that you knew exactly what you were doing. So keep in mind, rice tables are just a key component to solving any kind of equilibrium problem. All right, if you have any questions or need any help, please feel free to email me. Bye, guys.